Hello and welcome to our webinar. My name is Tracy Berardi, Program Director of the Consortium for Information and Software Quality. At CISC, we develop standards to automate software measurement, and we also enjoy hosting educational events throughout the year. So today we're sitting down with Dr. Greg Law, co-founder and CTO at Undo. This year at QCon London, Greg presented a talk, Record, Replay, Rinse and Repeat, Easily Rebuilding Programmatic State. And drawing from QCon and some of our conversations with Greg and team, we're going to look at how reverse debugging and recording technology can help us respond to failures in production and test environments. So Greg has offered to walk us through some of the history around computer science, bringing us to the implementation of record and replay systems to debug software to the root cause. And this is possible today by taking advantage of advances in compute, network bandwidth, and storage costs. So this will be an interesting talk. We have about 30 minutes. And in the handouts tab, there's a couple of resources, including slides from today. And of course, we'll save this recording and post it to the CISC website. We have the link here up on the slide. So Greg, thank you so much for joining us today. And I'll go ahead and pass presenter control over to you to get started.
Awesome, thanks Tracy. So here we go, share the screen, and I'll put some slides. So hopefully we can all see them, and I just need to figure out how to get this to the top. Just one moment. Whoops. Okay. Oh, I've got. That's better. Okay. All right. So slides just loading. Yeah. So how we can use software failure replay to a new technique to allow you to understand what software has really done. So I'm going to start with a bit of history here. We're going to go back to kind of the beginning, arguably the beginning. I think you could. It's always a tricky thing. Who was the first programmer? I mean, Ada Lovelace, of course, has a pretty good claim. Maybe even the people who programmed the looms in the early Industrial Revolution also. But this chap here, Maurice Wilkes, I live in Cambridge. He was down at Cambridge University in what was then the mathematical laboratory, and I think he has pretty good claim too, because he was the first person to write code on a computer that we think of as like a modern computer, right? An electronic computer, stored program, executing stored programs from memory. And he was the first person to write code to do a real thing, right? So he's actually solving a problem. It was a biology problem. It was kind of a sort of forerunner of genome sequencing, and he realized that one of these newfangled computer things might do it. And in his memoir, he says that he remembers the moment when he realized that a good part of the remainder of my life was going to be spent finding errors in my own programs. And anybody who's embarked on a career in software will probably have gone through that same realization, and you might even remember it. I remember realizing that when I first started out. In fact, my daughter, when she started programming in Scratch a few years ago, she said to me, Dad, I quite enjoy it. It's lots of fun. I enjoy it, but I have to do it a lot of times to get it to work. And I was like, yeah, that's, welcome to programming. And when Maurice was working there, he wasn't using the term debugging. And actually, here's a myth buster. So popularized or first sort of introduced with Grace Hopper and her team when they found this bug in the system. Actually, I like to sort of dispel these myths. It's a common myth, and if you look at there's a picture of the logbook here, and you look right underneath that moth, there's a note that says first actual case of bug being found. So you can see you can sort of tell from the humor there that actually people are already using the term bug and debugging back then. Actually, it kind of even predates software and programming, and Edison referenced it in some of his designs. But really, debugging is unlike anything else in software, right? Software is just this process of debugging, right? And writing software, is sort of, how many lines of code do you think you can write and have it work first time? I like to think of myself as a reasonably good programmer. What can I do really realistically? 20 maybe, if it's pretty simple, right? Humans just aren't very good at writing software. and that process of just getting it to work, this process of debugging, we sometimes call it inner loop debugging, just completely dominates the software development process. And it's kind of, when you just stop to think about it for a moment, not that surprising, right? I mean, it really is the ultimate needle in a haystack problem. I mean, a modern machine, even a single node on a single CPU core, is doing billions of operations every second. And you're perhaps looking for that, one bad operation that happens after, say, an hour or something. I mean, it's quite amazing that we ever managed to debug these things at all when you think about it like that. Let me give you a real example of a customer we started with, one of our early customers, Cadence. So you may well be familiar with them. They do the Silicon Valley company. They do the software that the chip designers, the likes of Intel and Apple and Qualcomm, use in order to design and verify their chips. And in this particular case, the simulation software was running with one of their big customers. They're doing a big chip design, so it means the thousands and thousands of regression test runs are running all the time using Cadence's software. And because one run in about 300, after about 8 hours of execution, Cadence's software would crash, right? Segfault. Now we've all, we've all kind of been there. It's not that unusual, but it's just a nice example of a really difficult thing to debug, right? Cadence actually had engineers on site with that customer for 3 months trying to get to the bottom of it. They were opening up a core file. There was a -1 where there should have been a pointer, but other than that, it's like different every time, and they're just getting nowhere. So it can be an extreme case like that, or it could just be, I've written some code, hasn't worked first time. I spend, an hour in the afternoon and I get it going, right? Whether it could even be less time, 10 minutes. So bugs take a variable length of time to fix, but we spend a lot of time doing it. Another way of saying the same thing, here's a nice quote from Brian Kernighan that I expect many people have heard, that everyone knows that debugging is twice as hard as writing a program in the first place. So if you're as clever as you can be when you write it, how will you ever debug it? Right? Nice little pithy quote, makes a lot of sense. Obviously, what he's really saying here is, don't try to be too clever, because you're perhaps not as clever as you think you are. And if you make your code, super sophisticated, then you're going to be in trouble. So kind of work within, have a margin for error. But there's another, I think there's a sort of corollary to this, if you think about what this implies, or an implication to this, perhaps I should say, which is that debuggability, if you will, is the limiting factor in software design, software development, right? Well, like whatever your metric for good is in your program, whether it's how fast it runs, or how featureful it is, or how extensible it is, or how quickly you can produce it, whatever your metric for good is, if you can make the debugging better, twice as good, then you'll be able to make that metric twice as good, right? So debuggability is the limiting factor in software development. And it's just something that we kind of just accept, right? Because it's just so dominates any programmer's life so much. It's just like part of the job. But I think we can do better, and we're going to get into some exactly kind of how we can use the technology to help us. So what is debugging? Another way to think about debug, or sort of way to express debugging, is this process of what happened, right? What did the software do? I wrote my program, I had certain kind of mental model expectation of what it would do, and reality is different from my expectations. And so where did it diverge from what I expected? And one way you can think about what makes bugs hard is you've got these kind of two axes, right? So there's the time between the root cause of the bug, the actual bug, and the time you notice, right? So the assertion fails, or there's an unhandled exception, or whatever, or you generate some bad output, whatever the manifestation of the bug is. How far before that, how many millions or billions of instructions have executed prior, between the actual bug and anybody noticing? And obviously, the longer that is, the harder it gets. And then the other axis is this repeatability, right? Determinism. Does it fail in the same way every time? And if it does, even if it's quite a long time between the root cause and the bug, you can just keep going. It's a painful process, but you can keep running and keep extracting more and more clues, a little bit of information about what's happening. But like in that Cadence case, I said, that was like up here in the top right. Okay, it was happening. It was the root cause was hours before the actual bug struck, and it was completely different every time. So two runs, you couldn't rerun and get more information at different times. Then it becomes like almost impossible if you're up here in the top right, or the further to the top right you are, the harder it gets. So now I'm going to get a little bit autobiographical, and so back in sort of 2006 time, I came across this thing called the omniscient debugger, right, the all-seeing debugger, and I thought this was really interesting because we've all used debuggers, and they're kind of useful, but they don't really help us answer that key question to debugging of what happened. They can allow you to stop a program, peer around, run it forward, maybe a line, run it forward, maybe to a breakpoint. Okay, what they do is they slow down the execution of the program, right? You deal with your billions of instructions every second by kind of having it in super slow motion, and you can kind of peer around. Well, the omniscient debugger gives you control of time as well, and lets you not just step the program forward, but step the program in reverse. Go back a line, go back 100 lines, go back a minute. See exactly what just happened rather than trying to figure out what happened by seeing what is happening, right? Much more direct way to get the answer. So it's a pretty cool piece of tech. And then I looked into this, I found actually this was by far the first, and there are actually research papers on this going back to the 1970s, and countless PhDs trying to do this kind of thing, right? And it turns out to be, it's actually when you don't have to think about it too hard to realize this would be a really powerful thing if you can make it work. Helps you answer that what happened. But I'm going to talk now about the implementation of these things and why, just really in the last few years, it's changed from being kind of, all technology all important technology starts off as what looks like a toy, right, or a demo before it sort of becomes real. And I think we're seeing that with replay debugging, with software failure replay right now. So what happened? As we said, that's the key question in debugging. Well, another way of asking that question is, what was the previous state? Slightly more specific question to ask my program, right? So let's think about if we're gonna make a debugger. You know what I'm going to do? I'm going to stop there, and I'm going to switch to show a demo, because I think it's going to just make. I meant to do that, but I think it'll make a lot more sense if I switch to show a demo. So just bear with me while I switch over to here. And just one moment. There we go. Okay, that's not supposed to happen. Just bear with me. I've just logged off that system. That's annoying. Don't know why that happened. I'm just going to have to connect back to my system to show.
That's okay. Take your time.
Yeah, we'll be there. Just 1 second. So 5266. This is because I'm usually using Linux, and the webinar software doesn't let you join using Linux, but doesn't let you kind of present using Linux. So I have to remote into this system here. So here we go. So that is now working. Good. I'll get that out of the way. So I'm actually, you might notice this if you ever see the background, I'm actually using my son's Windows computer in order to show this. So he's being very patient. Right. So here's my little demo. So I've got here a Jenkins setup. It's pretty small, and the demo I'm going to show you is very small, but this all scales to really large applications, like whether it's Cadence's software or SAP HANA or Juniper network switches. So, but small demos just because that's what you need in order to make it easily understandable. So here's my little Jenkins pipeline. I've got this is a sporadics farm, right? So I've set up Jenkins here to take the tests I have that fail sporadically, intermittently, and just run them again and again with this recording turned on, and it generates some artifacts. Typically in Jenkins, when you have your artifacts, what you get is it's a kind of you get some log files. If you're lucky, maybe you get a core file. Well, what we've got here is these .undo files, which are these recordings of the program's execution. So I can just download that artifact, and then I can load it up into the debugger here. So this is kind of, at the moment, this is kind of like looking at a core file, if you're familiar with that. And I can see here, I'm kind of, this is my backtrace here. So actually, I've shown I've stopped this at 0, but if I look a bit closer, I can see that actually it's inside the machine code of the C library, right? It's just the C library that was running on the test system, doesn't have any debug information with it. That's fine. It's captured all that down to the instruction level, but I can reverse step out, which is kind of an uncall button, if you like. Go back to the call site, keep going back, now I get to my code where I do have some debug information, so we can start to sort of debug this symbolically. So this is what I was talking about before, right? This is the magic. This is the first piece of magic that we'll see here. I'm gonna this is like a core file. This is a program that ran some time ago in my test system. But now what I'm going to do is do this reverse step, and I'm going to go back a line, right? And notice the data here as I go back. So I can just see what just happened, right? I don't have to try to like infer what happened. So now I've gone back to let's have a look what's going on here. So sorry, I should have just gone. Let me just go back to where we were. I've gone this slightly out of order here. So it's gone to this assert 0 because square root cache is not equal to square root correct. It's called this function cache calculate and passed in number. Number I can see here is 255, and it supposed to return the square root, and it's returned 0. Right? Obviously 0 is not the square root of 255, so that function has returned the wrong thing. So I now need to know, well, why? Why did that happen, right? So if I go back to where I was, I'll go back here, and now I've gone just after that function returned. So now I can reverse step into and see why that function returned what it did. And I can see here it's returning from this cache. It's returning the ith entry in the cache. I can see down here that I is 8. So it looks like my cache contains bad data, and if I look there, sure enough, it does. It's saying telling me the square root of 255 is 0, so the cache contains garbage. So as a programmer looking at this kind of issue, this is a bad day at the office, right? I've got some kind of corruption in my data structure, and I don't know, like, is that caused by, is it a pointer error? Is it a threading problem? Is it a logic error? All I know is it contains bad data. I need to know, how did that happen, right? So what I'm going to do here, and this is the second piece of magic, is I'm going to can't quite hang on a minute. I've got to get that so I can see that screen, run out of screen real estate here. Just bear with me. I am going to. I still haven't got that screen real estate. Just 1 second. Gah. I've got this in present mode, so it's nice and big, but it means I don't have enough pixels on my screen. So add a watch point. So this is like sometimes called a data breakpoint, right? So I'm going to add that there, put this back where we were so we can see. So I put a watch point on this data here. And normally a watch point, you set a watch point in debugger and you run forward until that data changes, which is kind of useful, take you to some places interesting. But what I'm going to do is run backwards until the data changes, right? And that takes me right back to the line of code that most recently updated this data structure, which is probably where I want to be. So I click this button. Boom, right, I've gone back in time. I've gone back in time to when the data structure contained good data. Square root of 140 is 11 with integers. Actually, I can, if I just like go back, if I go forwards here, then we can see, wait a minute, whoops, sorry. Why is that doing that? So, I'm not sure what's going on there. That's the first time that's ever done that. Anyway, that's great. That watch point take me back to where the data was modified. I can go back to where that data changed. I can go straight back to get to the root cause of that bug. I wonder whether I've got some line number mismatches on this code. I think that's what I've probably done when I was messing about there. Anyway, that's gone a bit, but you get the point, right? So I get control over time. I can step forwards and back. I can go back to when data changed. I can follow the flow of my program. So let's stop sharing that. Go back. So that's what this stuff looks like in practice, right? And if I take you back to that cadence example I spoke about just now, right? So that they have engineers on site for 3 months trying to get to the bottom of this problem, memory corruption, and it's different every time. So after 3 months, that's when they turned to us. They installed Live Recorder. They ran it, recording their application. If you remember, it failed after 8 hours, one running 300. So they just left a bunch of them going over the weekend, came back in on Monday morning. Sure enough, a couple had failed. They took one of the recordings of the failure, loaded it up into the debugger, set the watch point, just like I did in the demo there on the -1, ran back. It actually had to run back for 3 hours because that's how far in the past the actual corruption happened. But once it had run back, it went to the root, the root of the problem, and they had the problem fixed in a matter of hours, right? So they'd gone from 3 months, well, actually they'd gone from infinite time because they were getting nowhere, to having the thing fixed in just hours. And that's lots of cases of that. Although I also say, if you can routinely turn an afternoon debug session into 10 minutes, that's like perhaps less glamorous, but actually turns out to be even more important in terms of the overall productivity win, if you like. So let's try to think a little bit about, let's talk a little bit about how you do this. How does this work? How do we make this magic happen? And we're going to step back a line, and we want all the state to go back to what it was. So we're asking this question: what was the previous state of the program? Well, if you think about how you're going to implement this, well, there are really two ways you can do this, right? First thing is you can just save it. You can have some kind of transaction log. Every piece of state that my program changes, I'm going to squirrel away that state change somewhere. Just going to change it. I mean, just all the delta, right? I'm not going to store the whole thing, but that's going to then be enough that I can go back to any preceding state. But we just discussed programs run at billions of operations every second, so that's going to generate like a lot of data. And for that 8-hour run I just spoke about, that's really not going to be practical. It's also going to run very slowly. So lots of the PhD implementations of this, the omniscient debugger did this. I just recorded every state modification of the program, but that's it doesn't scale, I think, is the point of that. It makes some nice demos, but you could probably do my little cache calculate example I just showed just now with that, but it doesn't really work for real world applications. So the other thing you can do is to recompute it, right? I can recompute my prior states, but that's you don't have to think about that too hard to realize that's not so easy either, because some of my statements, if I have a statement like this, right, and I've just executed a statement like that, I can work out what the preceding state of the program was very easily. So, that's a kind of reversible operation, but that turns out to be quite a minority of the things that, and most statements look some bit more like this, and that's not reversible, right? The value of A after that statement, the prior value of A is gone, doesn't exist in the universe, right? Information has been destroyed. Actually, there's some really interesting work going on in some sort of computer science departments around making reversible hardware, reversible logic, such that you can do that. And that's not actually that's motivated as much by energy saving as debuggability, right? Because it turns out that process of destroying information takes energy, and a lot of the heat that you have to get rid of in computers is sort of directly as a consequence of that. There's a theoretical limit to the amount of minimum to the amount of heat that you have to get rid of based on the information that you're destroying. So if you can make the logic reversible, in principle, it can run with lower energy. So that's all kind of interesting, but I think decades before that stuff really hits commodity hardware. All commodity hardware today is fundamentally not reversible. But there is another way to recompute it, right? Which is that we can kind of do a combination of the two, and we can re-execute the program. So in that little demo, when I'm going back a line, what's actually happening under the hood is it's going back to a snapshot and playing it forward to just before where I was, right? And all the state gets updated. And that works because computers are mostly deterministic things, right? If I rerun a program multiple times and I give it the same starting state and I feed it the same set of inputs as it runs, it's going to do the same thing. So I can exploit that, and that's what the technology does. Catch is, though, that you can the computers are deterministic except when they aren't, right? And lots of things make them non-deterministic, and that's, if you remember that thing of what makes bugs hard, is the top right of that quadrant. That's the that's the non-determinism. So what things make computer programs not be deterministic? Well, any kind of input, right? Any user input, any input from the network or the file system or anything like that. Threading and timing issues make things non-deterministic, of course. Accesses to shared memory, there's asynchronous signals, there's some instructions actually turn out to be non-deterministic. So there are actually, as it goes, multiple sources of non-determinism, but these are relatively rare. Mostly what the computer is doing is like adding two numbers together and storing the result somewhere, and that damn well better give you the same result each time, otherwise you're really going to be in trouble. So we can actually store just a tiny fraction compared to if we stored all of the state transitions. By storing just those non-deterministic inputs, it's much smaller, actually turns out, very, depends a lot on the program, but this turns out to be something more like a few megabytes per second of recording if you're doing this, and so this allows us to really apply this approach at scale. So we have this event log. We actually do use this in the undo.io. We use this in-process virtualization technique to allow us to get in a lightweight way and capture all of that non-deterministic state. But I said at the beginning that this is a thing. There are multiple implementations of this. I think this is a technique really whose time has come. And so live recorder, that's what we do at undo.io, and we just saw the demo just now, and it works with C++ and Go and Java programs and some others as well, but those are the main languages that we support right now. There's an open source thing called RR, which is pretty good actually. It stands for record and replay. It's quite a bit sort of more lightweight, smaller thing than what we do, and it has sort of limitations in where it will work, but where it does work, it works very well. And there's a thing inside GDB, if you're familiar with that, which they call process record, which actually does the technique that doesn't work very well, right? That's the transaction for every single state change. So it's extremely slow and takes a lot of space, but it does work. If you wanted to have a play with this on a kind of small program, then you can experiment with the GDB process record stuff. But live recorder and RR both use this technique of just storing the non-deterministic inputs and then recomputing prior states. So that's all on Linux. On Windows, Microsoft are quite getting into this in quite a big way, actually. So they kind of brand it time travel debugging. So there's time travel debugger for C++. There's one at C#.net infrastructure. They had one in Record JavaScript, although actually they've just kind of switched their JavaScript engine. So I'm not quite sure what state time travel in JavaScript in Microsoft land is in. But they're pushing time travel debugging, as say in C++ and in .NET pretty hard now. And there's another startup company like us called RevDebug, also on Windows, for C# and Java code on Windows. So I'm sure I've missed some. If you're more of an embedded person, there's sort of hardware assisted things that have been doing this for some time. Green Hills Time Machine type stuff. I'm talking about software implementations of this, but if you have the hardware to help you do it, you can kind of do the same thing. The Lauterbach debugger does the same as well. So across different platforms, there's different technologies to kind of give you the same kind of power. So that's it for the talk. We'll run just a little bit longer than I was expecting, but we do have a few minutes for Q&A if anybody has any questions.
Great, thanks, Greg. There was a question, but you just answered it with this slide. Actually, there's a question about an example was in C++, what other languages are supported. And then there was a comment from our friend Carlos, good luck with the laws of thermodynamics. Is there anything in Mac OS?
No, that's missing, at least. I'm not aware of anything, at least. I think that's a gap that needs to be filled by somebody, whether it's Apple themselves or someone else.
Okay, great. And I'll just remind. And he said, new business opportunity.
Yeah.
And so, okay, here's one more question. How do you monitor when an exception occurs?
Yeah, so I perhaps should have specified that this is all running at user level. Now these techniques I think could be applied down at the kernel or for embedded systems, but you may need certain hardware support. But at user level, okay, there depends what you mean by exception. So if it's a language level exception, C++ or Java exception, then for this technology, that's it. Actually, it just works, right? Because we're working at the instruction level, and when the language is generating an instruction, it's just generating an exception. It's a sequence of instructions, right? And that's all we see. So we're kind of completely ambivalent, agnostic to that. You can, inside the debugger though, you can put exception catch points. So you can say I want to stop when an exception is thrown. And in our Java product, you can actually say, take me to where this exception was raised. If I've got an exception object in my hand, I can just go back to where that got thrown. So it's quite good support for language level exceptions. For kind of hardware level exceptions, like asynchronous signals, that's one of the things that our in-process virtualization technology does. So we've got enough kind of hooks into the OS that you can actually get the program. You can use a thing called ptrace, which basically allows the program to be stopped whenever an external exception occurs, and then we can do whatever it is we need to do in order to store that in our event log.
And then the last question that came in, how can we get these techniques embedded or folded into test-driven development from the point of view of what the devs, programmers have to do, workflows?
Yeah, really good question. I mean, what we found is that it's if you want to get, if within an organization you want sort of widespread adoption of this quickly, then you have to be embedded into that workflow, right? And it depends, most software development organizations have pretty sophisticated workflows. They've got their CI pipelines, and they've got whatever unit tests, and quite a rich kind of world these days for the most part. So yeah, it's one of the things that we've done with Live Recorder is to make it explicitly kind of embeddable, right? So it comes in different forms. One of the forms that comes in is kind of library form, and you can link that into your application. And the other form it comes in is kind of an external monitor, so you can put it into your CI system and have that monitor application. So yeah, a bit of plumbing to do, but we've deliberately made it kind of flexible to be able to do that. I showed a little example of how we've done it in that little Jenkins kind of toy demo. But yeah, integrating into the workflow is really important, because as a developer, you don't want to context switch away from your regular flow onto something else, right? You want to be able to do that kind of seamlessly within that workflow.
And then Greg, if you have a moment for one last question. These techniques have a lot of potential for info security. What do you think about that? Yeah,
I think that's a really good observation. So if you think about this from a high level, as I said in the slides, this is really answering the question of what happened, right? And there are as a software developer debugging code, it's a what happened question. But as a kind of infosec point of view, there's also that question of what happened, or even actually what didn't happen, right? So one of the things is this is complete. This completely captures the process. We can go back to literally any instruction that executed and see any piece of state. So you can also, to take the flip. So can you verify that during the recording of this application, it did not, open a socket to this particular bad domain, or copy this file around, or did it ever have this information in it? So you can actually prove negatives as well, which is really interesting. The other thing I think from an infosec point of view, and this is something that's been I think really quite underserved. If you could draw that, it's always a bit dangerous, but draw the analogy between physical security and kind of cyber security. In the world of physical security, of course, we have ever more sophisticated locks and gates and fences to keep the bad people out. But more and more now we also have CCTV, right? We have ways to, well, we accept that however hard we try, somebody sufficiently determined, they will get into the building. And so we want recording of that so we can actually see what happened, who came in, what did they get. And in the kind of virtual world, because lots of investment goes into, ever more sophisticated locks and preventative cures and measures, and that's all good. But there's very little around actually, monitoring, right? And being able to answer what happened, who came in, often after there's been a breach, you don't even know what they got, right? So I think this has great application in there, but I think it's a little bit early, to be totally candid. So I say this is a technique whose time has come, and when it comes to debugging code, whether that's during development or in test or in production, then this technology is definitely up to that and doing that all the time now. When it comes to security, when you're a bit more of a kind of always recording, just in case type deployment, I think in full candor, I think none of the implementations are really sufficiently mature to do that, particularly in terms of runtime overhead.
This is great, Greg. Thank you so much for all of this information. We're going to capture this recording and slides, so I'll send a copy to everyone either later today or tomorrow morning. And Greg, if you're up for it, I can include your contact if folks have some more questions.
Oh yeah, please do. Yeah, absolutely. Yeah, always happy to talk about this for as long as anyone will listen. So yeah, please do.
Great. Yeah, there's a lot of good comments coming in. I'll share those with you too.
Yeah, awesome.
So thanks again. And even some folks logging in at 2 in the morning. So appreciate everyone's time today, and have a great rest of the week. We'll see you soon.
Okay.
Thanks.
Bye. Bye, everyone.
Bye-bye.